Hello, good morning, everyone. So, welcome to the International Conference on Future 6G Systems and Behind. This conference also became an IEEE Institute of Electrical and Electronics Engineers International Workshop with the same designation, Future 6G Systems and Behind. We are delighted to have each and every one of you here today. This event has been organized by a coalition of esteemed institutions, namely Universidade Autónoma de Lisboa, IEEE, Instituto Superior de Ciências Policiais e de Segurança Interna, Instituto Politécnico de Tomar, Centro de Investigação em Cidades Inteligentes, Autónoma Tech Lab, our research center, ICPOL, Fundação para a Ciência e Tecnologia, and the European Agency for Policies, Europol. Thank you for excellent collaboration. Your commitment to the advancement of 6G systems and beyond is truly commendable with your cooperation in organizing this event. This conference serves as a platform for sharing knowledge, ideas, and experiences related to cutting-edge trends and innovations in 6G and its future horizons. By facilitating collaboration among researchers, industry professionals, and policymakers, we aim to advance the development of 6G systems collectively. While the requirements of 5G were fulfilled through millimeter wave communications and massive MIMO, multiple input, multiple output, 6G systems needs the integration of novel concepts, including large intelligent antenna systems, LIS. In terms of frequency bands, 6G is truly revolutionary, embracing terahertz bands, that is ranging frequencies from 100 gigahertz up to 10 terahertz, thereby enabling data rates of the order of terabits per second. Our program encompasses 4 talks, each covering the different aspects of this field. It is an honor to have all of you, namely Professor Shahid Mumtaz, a distinguished lecturer of IEEE Vehicular Technology Society, and Professor Rui Diniz, a distinguished speaker of IEEE Vehicular Technology Society, as well as our speakers. As we embark on this conference journey, we hope you find it both productive and enjoyable. Thank you all for your participation and valuable contributions to the advances of 6G systems and beyond. Let us start this conference with enthusiasm and a shared dedication to shaping the future. Thank you very much. So the first speaker today will be provided by Professor Shahid Mumtaz with the title of his talk is 6G Vision Requirements, Technical Challenges, Standardization and Implementation. I will read his short biography. Shahid Mumtaz is a IET Fellow, IEEE ComSoc and ACM Distinguished Speaker, recipient of IEEE ComSoc Young Research Award 2020, IEEE Senior Member, founded of EIC of IET Journal of Quantum Communications, Vice Chair Europe Africa Region, IEEE ComSoc, Green Communications and Computing Society, and Vice Chair of IEEE Standard of P 1932.1, Standard for Licensed and Unlicensed Spectrum Interoperability in Wireless Mobile Communications. He has more than 15 years of wireless industry academic experience. He has received his master and PhD degrees in electrical and electronic engineering from Blekinge Institute of Technology, Sweden, and Universidade de Aveiro, Portugal, in 2006 and 2011, respectively. From 2002 and 2003, he worked for Ericsson and Huawei at research labs in Sweden. He was with Instituto de Telecomunicações and is now full professor of Nottingham Trent University, United Kingdom. He's author of 4 technical books, 12 book chapters, more than 300 technical papers. He had supervised several PhD and master students. He uses mathematical and system-level tools to model and analyze emerging wireless communication architectures, leading to innovative masters, theoretically optimal new communication techniques. He's working closely with leading research and development groups in the industry to transition these ideas to practice. He secures the funding of around 6 million euros. Shahid, the floor is yours. Thank you very much for being with us.
On 6G vision requirement, technical challenges and standardization for 2030. The main idea behind today's talk is to give you the brief introduction about what is 6G and what are the requirements, especially in the standardization, and what kind of technologies we are looking into 6G, which will be shaped from now on around 10 years of time, 2030 or 2032. But I'm not going into more technical detail because there is a more presentation will coming, like mentioned by Mario, millimeter wave, massive MIMO. They will go in more detail on specific technical challenge. Okay, let's start now. Okay, so before going into the deep depth of the 6G technology, it's important to understand how we start our journey from 1G to 6G, and what are the technologies and what are the challenges which we shape around this journey. So in telecommunication sector, mostly after every 10 years, we change our generation, and most of the standardization will happen after every 10 years. So if we say roughly from 1980 to 2030, when we start with our first G, and then we end at the 6G as well. So if you see around 1980, when we start our network, so-called, which is wired network, we're starting with human machine interface. On that time, we don't have keyboard, mouse, but there is the interface which we're going to communicate with the network. And then we have the hardware on top of that. Then we have the operating system. Then we are running different apps, and we have a network, and we have an AppNet, which is mostly used on that time in states. So you can see the different colors labeled with valued and devalued, and you can map according to their significance in that year. Then after 10 years, we move toward the more human machine interface, where we have mouse, keyboard, and now we start to interacting with our network. And then we have the hardware, and then we have same like operating system application. And the most important part is the AppNet. Now AppNet is converted into WW when people start using World Wide Web, and they start browsing some of the website, not a lot, but now they start using the browsing, and our network also getting some importance because we start building a core network with the fiber and etc. Then after 10 years of time, when we went into the real mobile communication era, and our WW convert into telco system. This is a time when a lot of mobile operator, not so much on that time, but which was available. They tried to see the importance of the internet into their telco system. So they start building their system with the internet connectivity on that time with different core, like ATM on that time was quite famous. And then network get a lot of important, lot of people start working on core part of the network, like switches, routers, and they start connecting and try to make the telco system. And also we came up with our first mobile handset from Nokia 3310 is quite famous on that time. And then the bottom one, you can see that some are valued and devalued. Then after 20 years of time, when we enter especially into the era of 5G, when you can see that our telco system now we converted to webs and cloud of systems. So you can see that now a lot of mobile operators using clouds now, a lot of services are running into the cloud. So network gets some value or devalued, and now you can see everyone using very smartphones. It's touchable and everything will be inside one box now. And you can see that at the bottom there are some valued as well. Now what happened in 10-year time, now you can see that our cloud system is mostly going toward the data centers, and of course the work has been started, but you can see a lot of application will be run there, a lot of DSPs running there as well, processing part, and network is more like a passive pipe, and the holographic communication, you can see that is changing as well. And our operating system will be virtualized, a lot of virtualization will be happen. And at the hardware level, mostly this is the very basic RF part, and all the processing will be done in the clouds. And human machine interface will be more kind of holographic communication, where you teleports human being from one place to another. But that is a futuristic thing. So this is a timeline that can be go beyond 2030, but that is where we are heading toward. So today we mostly talk on 2030 portion, that one, where we talk today more on the digital twin, metaverse, and what are the technologies which really shape this only all at the physical layer, Mac layer, and upper layer technology, because all these technologies can contribute to make this 6G to be 6G possible for the future systems. So on the handset side, seeing it's also we see the network side, but it's also see the how the UE sides, the user changes over the years. If you go from left to the right, you can see that the sizes of phones are quite big on that time, where you use only numbers like Ericsson using 1970s, and you can see that they have very big transistor size, about 12 nanometer. But when you go from left to right, your transistor size are getting smaller and smaller. So like Samsung now is S7, S21, they use transistor size of around 4 nanometer. So we have a limit. We can go beyond that on the according to Moore's law. But you can see that we go and see the more efficient communication we get, the more services we get. But again, it's more power hungry. Our devices are getting more power hungry because a lot of apps are running. So we need to come up with more sophisticated technologies on all the layers with more optimization stuff as well. So you can see in this picture, we are almost on 5G, where you can have this phone now from, especially from foldable from Samsung, but in 6G mostly on tactile, like holographic, where you can even sensory kind of information along with voice data. You can also feel, touch, smell kind of information can be transmitted over the radio links. So more or less, most of the companies in 3GPP release 19, the workshop happened, and now they're going to release new document at the end of this week. And most of the companies agree that the trend toward 6G will be on connected machines, where you have the machine as the main users. We have the AIs, machine learning tool. AI is not a new area. It was in computer science for many, many years. But now how to implement at wireless communication, especially at physical layer, is quite challenging. Machine learning was using in 5G as well, but mostly on the upper layer. And now the openness of the mobile communication, that we need to make our network openness. Like we are using SDN, NFV as a core part. We are also using the Open RAN, this kind of system, but we want our network is open. So that is the big challenge. So this is the step toward Open RAN and how to standardize this open network. So any vendor can use any software, or any software can use any other vendor hardware as well. And then the last one is the social goals and mobile communication. This part is quite new because of the way the frequencies of the application we are developing every day, and the ethical issue. We are using a lot of machine learning, so we need to create kind of standardized ethical goal and social, which can not only for the machine but also for the human, the way we are using. So toward that, a lot of work have been done in European Union as well, and also in states. They are also going to standardize things on this. But in this presentation, I will mostly talk on first two bullet point, because I don't have enough time to talk last two bullet point. Okay, so let's talk, think about the past, present, and future of our network. So if you can see that when we change our generation from 1G, 2G to another one, we need to come up with the new use cases. That is the main target. Like, for example, if you can start with our around 2000, when the main target is to move the data, how you transmit with the web, application, multimedia. On that era, the most important time till now that we are trying to enhance, we're transmitting only data and voice over the network. And here we need around medium kind of latency, medium reliability, and medium throughput as well. But when you come to 2030, this area where we are looking more like what we call beyond 5G, we have this enhanced mobile broadband, machine type communication, and URLCC, ultra reliable and low latency communication as well. And here we need around with voice and data, we need also the tactile as well, where we need to transmit some of our sensory feelings kind of information for the, and here we need a very low latency, high reliability, and high throughput. Reliability and throughput is easy to achieve, but the big challenge is how to decrease the latency of the network. This is a quite hard challenge in the network because of latency coming from different factor. If you see end-to-end latency of the network, then beyond 2030 plus, when you see after next decade, where the real 6G, you can see but the target will be on that time. The use cases will be quite different. It will be a new media when we need a holographic kind of simulation, new services. We need teleports, like you're teleporting from human beings from one place to another. We need a new infrastructure as well. And on that time, you can see that along with the tactile, we also need a holographic kind of information where we have quite low latency, quite high reliability, and high throughput as well. So before going into the 6G, it's very important that what we achieved so far in generation starting from 1G to 5G. We work a lot of people are specialists in that area, a lot of companies, researchers, scientists, they did a lot of hard work, and now we are able to see the real fruit of 5G. But most of the solution which we developed on that time and still now, we see network only two nodes, either is the base station or on the UE. So we will develop our solution for either for uplink or downlink and try to optimize whatever different solution is it. So more or less we take a narrowband kind of approaches which are partially fixed or dynamic. But when you go toward 6G thing, so everything will be dynamic, and we are entering into different world. It's one is physical world, one is the virtual world. The virtual world is the world which is created by the human being, which we called a world where we use a metaverse kind of thing, digital twin, XR, VR, which are the sub use cases of the big metaverse. So in this world, everything will be dynamic. And why we need that? Because we want more sophisticated solution for our future society. So that's why we not only emphasize this our real world, but we try to optimize the virtual world, which is directly connected with both of them. And our verticals are changing. We are not developing solution only for the user, but also with the different industrial sector, can be finance, banking, and industry 5.0, vehicular, and directly optimization of world. So you can see that the big challenge is here, how to connect these two worlds with high reliability, low latency, and high throughput, and also the optimization as well. And you can see a lot of big data can produce, a lot of machine learning algorithm will become to optimize these two worlds. But again, these two worlds will be connected with a very a high-speed link, which I just mentioned, and that will be the help of 6G technologies. So why we need a machine when you go into the virtual world? We need to connect. Why we need machine? Because machine can do everything which human cannot do. Human have some limitation at their physical abilities by birth-wise. For example, human cannot see more than 500 megapixel with his eyes, but you can create the telescope, microscopes, which can see your organism and which can see beyond the universe with this high accuracy. So that's why we need the machine. So this is the distinguish between what are the differences between machine and the human being. So if you can see that after the Second World War, when Shannon come and they produced their this famous Shannon formula, and they use this SNR from till then till now, we are using inferring kind of communication, which is very sequential wise. We have a source, we have a transmitter, we have a noise from the channel, and we have a receiver, and we have a destination. So a lot of work have been done. We have very nice closed form expression for all of these things. So we are expert in this communication and model. We've done a lot of work at the transmitter side, where we produce from 1G to 5G, MIMO, single user MIMO, multi-user MIMO, a lot of things. And then we propose different cancellation technique, how to remove the noises, and nowadays using intelligent reflected services along with other technology. And on the receiver side, we have also a lot of nice noise detection, removal algorithm, zero forcing, MMS, SCA, along with other. So we are quite good in that. We know how this communication works, and especially at till 2020, but there is a work have been started already sorry, on the AI and machine learning as well. So the main target is how we can use at the bit level or at a symbol level. So you can see that in this structure, we have a transmitter, same like this, we have the noise, but on the receiver side, we don't need any destination, because here is the learning part. Like in the normal communication, you have a feedback channel, you have CKI, SNR, decoding matrix, PMIC, rank indicator, you send, if you talk about a MIMO case, but here you don't have any feedback challenge. This feedback goes until your receiver will be efficient enough to make their own decision. You can think like parents and kids relationship. So your kid after 15 or 17 or 18, he can make their own decision. Similarly, like this, so he can feedback until he's have enough data to make their own decision. So of course, once he has their own data enough, he can make their own decision. So he don't need any this channel from the transmitter. Of course, if there is something happen, he always asks the transmitter to update the data. Similar like for kid, if kid is if kid don't know anything, he always asks the elders. So they have another information update, and then they make their decision. So I will not going to make details here, because they have different algorithm on machine learning supervisor, reinforcement, regenerative, a lot of stuff have been done. But here the main idea is that how to use at the bit level. But the main target now is how to standardize these stuff, because this is a challenge in 3GPP, that what signaling, what are the interfaces which we need to standardize, so that different companies can, or different researcher can have one standardized interfaces which we can use for the to train your receiver, if you talk about downlink, of course. And then what are these interfaces name which should be standardized. Okay, so there's quite challenges, but I mentioned a few of them, which is mostly related to our domains at wireless communication. First, there's a lack of interoperability models between different. Nowadays, you need to train each of your devices. For example, you talk about your kids and these are parents, you need to train off her. So there is no interoperability model among neural networks. So we need to come up one model which can train all over the nodes, so we don't need to retrain again. And also, like Open RAN, we talk about a lot Open RAN, we need to become up with the open neural network exchange as well, so we can try to reuse that model as much as we can. So it can be run at your device level, which can be your RF part or your power management. It can be run on your localized elastic key or at the base station, or it can be on your transport link, can be fiber or copper, depending upon discipline, or it can be run at your core part as well. So it can be end-to-end AI, or whatever you operator or researcher want to feel, they can run there as well. But in the beginning, in 3GPP, there is a work done at a separate level. So it's still not end-to-end, but there is a working group working at the core part, which already they have this entity in the core part, which you can understand the AI microservices. But at RAN level, still they are what they have been doing now, mostly at the beamforming, load balancing kind of thing, where they are using the AI as well. So next topic, which is quite interesting, at least, which coming very hot topic now, is one of the use cases of metaverse is the digital twin, that we need to use digital twin. So the digital twin is not a new idea in the market. It was using before in this industry, but quite new in our wireless domain. So in the digital twin, mostly we do the replicable of a physical entity into the digital world, and then we take to the different advantage. So we can make digital twin of anything, can be industry, can be even in the human body. You can make a twin of human body, or can be of your cars. For example, you have a real car running outside, and there you have a virtual car which is running at your garage or your mechanic, and you are connected both of them with a very high speed. Just imagine we connected with via 6G technology, and then 24/7 the data is coming, and you can update that data, and you can see the performance of your car, especially as your mechanic, and he can easily predict what will happen in next 1 or 2 weeks. For example, if you use that Tesla or mostly the car with this electric, so if you have some problem, he can even update the software over the air, so your car is working correctly until they have some mechanical problem. But that is the main idea, that you need to optimize the performance much better with your 24/7 kind of twin running at any place. So it's just I'm just giving a short like a toy kind of this example. People, of course, is not from our area to understand how digital twin one. Just imagine if we have a city and we want to create a virtual digital twin for that city. What are the things which we need to do? For example, first thing we have to create with the buildings. Of course, just imagine we have a land and we want to create a city, so we have to create with a building. And then after building is done, then we have to put different kind of infrastructure, which can be a lightning, your sewerage, your pipes, roads, etc. And then we start your life inside a city. So that is the process which we are doing till 2010, I believe, when you have this kind of mobility pattern. Then there is a layer come, which we call digital layer or smart. So after 2010, a lot of cities, like I was living in Aveiro, so it's even my city Aveiro, we have tech city, so they have a lot of now access point sensors everywhere. which are connecting with the data, with a huge amount of data is coming around city. So we call this as a digital layer. But after 2020, you can see in future, now we are will be developed now. So you can see the new layer will come, which is called virtual or the digital layer. So this layer will help us to create the replica of our city inside lab or research center, whatever way you want to do. So you are getting your data at 24/7. So you can see that this is thing which are around 2010 and now it's 2020. You can see that is another layer come, which will help us to optimize our city. So this is like a template. So we can create, especially the same with our mobile network or for our industry every. So this is the structure which we need to create. So for that, we need a digital layer to create a virtual layer. So this is the more on this optimization, how our optimization work, which we just showed in the previous slide. So we need a real-time data. This is the digital data in constantly updating from our city. Just imagine this is our city of Aveiro, which you get the data, and then I will create that city inside lab because our data is coming 24/7. So city is planner, and then this implementation will go back. So this means I can easily optimize and monitor everything. And also I can predict in next 6 or 4 months what is the happening. If you want the humidity, traffic control, your path, everything is possible without going to the physically there. So this is just a template for the digital twin and how this works. So I will skip that slide because I think I'm getting out of time. So this is not same thing, but it's just for optimization. And then we have the digital twin that I just mentioned. So we need to Internet of Senses that we need to not only the data and voice, but also the smell, taste, the 6 senses of human being can also be transmitted from digital world to the physical world, but that is more beyond when you after 10 years of time, when our technologies are more sophisticated, where we can transmit as well. So all of these sector which I mentioned, media, internet, industrial internet, tactile, vehicular. So every sector have different kind of KPIs which we need to measure and the limitation. But the most important here to how to decrease the latency is the main target. Of course, we need reliability and throughput, but I believe they are easy to achieve. The most difficult is to how to decrease the latency. For example, in media, when you go from text to holographic, your latency will be around 20 milliseconds when you see the motion to photon without any blur. And similarly, in the from this industrial internet, latency around 25 microsecond to millisecond. Textile end-to-end is around 1 millisecond. Vehicular is around 5 milliseconds. So different sectors have different latency requirements. So we have to come up with different solution for them as well. One is, as mentioned, is the holographic communication. To transmit a human being, we need around a very high frequency, around terabytes of, because of the 6D, it's not a 3D, it's a 6D, which you transmit with your all the senses and all the human body, and you need to design the pixels accordingly and transmit it over the air. So it's quite high frequencies which we need, which is not possible now with the 5G. We have to move toward the higher band. But of course, then there is the limitation how transmit you can do because of the capacity and the coverage of that frequency band as well. So for that, we need to move from qualitative digitalization to qualitative digitalization. These techniques we are using a lot from 1G to 5G, because here the main motivation is to transmit text and voice. So we do very like physical layer, we transmit each and every byte. And if one of the byte will error, we transmit all the packet to retransmit, and we say this packet will be error and we transmit again. But with the qualitative digitalization, we cannot do this because we have to create pixel and human being, which is pixel. So if we lost something, we cannot retransmit whole human being. I mean, just a hologram, we just transmit that pixel. So this means no retransmission is required if we lost any byte. And for this is more application toward holographic and VR. It is also in the metaverse, you can see at least at physical level when you do the encoding and decoding. As very high throughput is needed for this kind of thing. So the main target, again, not now, but for future, we need to transmit all the human senses over the air, and whatever our human look like, we can see them, whatever in the house as well. So it's like nowadays we use Skype, but in the future we use a teleportation. So you can feel, you can talk, and you can also see the taste what he eating outside at your home. Of course, there is some target which we need to achieve. We have to go for around terabyte kind of communication, and latency should be 1 millisecond. But again, latency for me is very hard KPIs to achieve if you want to achieve all the sensory kind of communication over the air. So these are the few of the requirements. You can see nowadays a lot of companies and researchers are working on them to achieve all of these KPI. The inner circle is for the 5G, outer circle is the 6G. But I added this computational efficiency. This is, you can't see this in 5G, but I believe this is quite important as well, because now we are going towards virtual world. A lot of computational will be happening, and we are merging for our communication, and the computing world is trying to merge together to make more multidisciplinary kind of research and multidisciplinary kind of hardware as well. So I think computational is very important. So we need to more computing efficient as well. About the architectural changes, if you see the 4G, we have mostly cloud computing. So most of the computing will be done at the cloud or the core part. Our only wireless link is between BS and the UE. Then we move toward 5G, where distributive over the network. So then computing will be done as a part of the core part, cloud part, core part, and the BS, and our UE will be communicating with the base station. And our use cases, again, this is a very important because our use cases are changing. Now we have vehicular communication, IoTs, etc. But when we go to the 6G, as I mentioned previously, that we need to converge both of the world. So computing and communication. So this is a computing split over the network and device. So we can see that the part of the computing will be done by our UE as well. Of course, there's a challenge there because of the power consumption, but again, we use a lot of, here you can see that this federated learning, if you heard about this term, which do the modeling at UE and try to use a lot of machine learning techniques to make this more efficient because of the latency constraint as well. So why we need this kind of thing? Because our use cases are changing. So here latency are getting more, so we need very close to the network as well. Okay, so I think I have more over the time, so I will just skip that part. I don't have time. So I'll just go to the, sorry for that, it's quite a long presentation. I'll just go to the last part of the roadmap for the 6G. So far we are around in 2023, where we have some of the European call is SNS phase 1 or 6, phase 2 is finishing now, and 3GPP is also doing some kind of study as well. And you can see from here we are on the requirement on that part. So this is a roadmap constantly for everything. And this is the phase. Also, you can see the SNS will be phase around 30, and then afterward we will try to start deploying different POCs, like we did in 5GPP calls for 5G as well. And you can see the product will be around 2030, maybe onward, but this is just a prediction now. And if you see more specifically 3GPP, which is mostly doing the standardization since 2G till, so you can see that we are on the release 18 now, which are around beyond 5G, but still we don't call 6G yet. So 6G you can see after 20 release of 3GPP when they really define 6G specification. But here now different companies proposing different technologies, but most of the emphasis will be on this machine learning part along with other technologies as well. And then this is the more their timeline till 2030. So from my side, I think it's important I didn't have enough time to go through all the technology, but this is just a summary here in last slide that I called my network more like a liquid. So like a liquid can develop the shape of anything where you pour it, like if a glass or jug or mug, similar like this. So it can be of anything like our future network. So they don't have boundaryless, like called cell-free kind of thing, and anything can possible with this network. So it's not like a fixed one. So at device level, you need some of the certain technologies like virtual base station, multi-imagery, supporting graphene material. Actually, I had all this presentation, but I didn't explain you because of time constraint. And on the network side, you need like no boundaries, like cell-free, generic hardware. This is like a more on this open source kind of thing where every vendor use any other software and any software can use any other vendors as well. We have a virtual flying protocol stack, and this protocol stack is mostly unfixed. You can make your protocol stack over the air and over the dynamically, rather which we are using nowadays. Nowadays we have a fixed protocol stack, which I believe it will not work when you go toward more dynamic thing. And this can be a virtual Wi-Fi, virtual cells, virtual non-art, graphene materials, AI as well. And at the technology level, you need analog of DMA, like our air interfaces, cooperative coordination at network device level, non-coherent detection, cellular sensors. So these are different technologies which I feel that will be used in the network, but not now, but in next coming years. Zero energy at transport level, you also use a different MAC, fog, DU, blockchain, resilience, and at Spectrum, you can have your database of Spectrum. Nowadays, Spectrum is mostly owned by the regulator, but I believe that in future it will be more like a SIM card. So every operator, every machine, or every human being can buy their own Spectrum at certain point and also release them whenever they don't need. And we have cloud operator, mobile, virtual, and digital twin as well. And then at the user level, we have new users are coming, which is digital twin, machines, and human. At the antenna level, we also use non-uniform, non-structured antennas. We have done a work on that part as well, where we are proposing a new non-structured antennas as well. 3D beamforming, glass material, liquid crystal. These are all technologies which you can see in future on the antenna. And then on the business, because this is quite important for the operator to motivate them why they need this technology and why what is the futuristic effect on their business. So we need to propose a new business model, which is end-sided business model. And of course, we need a big insurance companies as well, which is provide the security that this infrastructure will work. If not, then we have to get our money back, and also taxi systems will be changed. Now we take taxis only from the human being, but of course, when you implement machine and digital twin, I think it's a good idea for the machines as well to have a taxi. So this is just my view on that. But that's all from my side. Sorry for I already 10 minutes over the time. So if you have some questions, please feel free to ask now.
Thank you very much, Professor Shahid. I don't know if there is any question. Yes, we have a question. Maybe it's better for you to use the microphone.
Thank you. So 6G technology has up until now been brought up to the attention of the public, mostly through internet memes. From being used to power government drones all the way to being portrayed as the Eye of Sauron from Lord of the Rings. Do service providers already have a strategy to counteract some of the cultural bias fueled by the technological illiteracy and inherent skepticism of the general public? Some way to humanize 6G and make it less akin to magic?
Okay, thanks. I mean, this question mostly more related to our business and social about that. So first, in 6G, there's the differences. We cannot have a red line, or we have a boundary line between service provider or the mobile kind of operators, because a mobile operator can be a service provider. But again, the coming back to your question about socialization, so that is the last point of my slide third, where I said that there is the talked on this topic which you mentioned on social, regulatory, and the mobile communication, because of things which you mentioned. One is flying base station or UEV, these drones as well. But for the time being, there is not such a roadmap for that. The reason is that we still don't know what is the 6G look like. We don't have spectrum band available. Maybe in the next World Conference, when they available some of the terahertz or more higher millimeter band, then we are more, we are more able to answer this question. But again, as you can see that when we start 5G in 2011-12, the same question will appear, that how 5G then take around 5 to 8 years to that. But on that time, we don't have these social policies or ethical, because on that time there is no issue of machine learning or other. But here there is an obvious point we have to address that this point. But for the time being, there is no clear roadmap how this will be done. But every service provider or the operator, for me, because for me there is no everyone do the same services nowadays. They do their alone models. For example, for security, for their own how they work. So there is not any standardized stuff. So everyone doing their own thing.
Is there any other question? No. So, Professor Shahid, thank you very much for your excellent presentation. Thank you.
Thank you. Bye.
So, right now it's my turn. I will be the speaker, and my presentation is entitled Transmission Techniques for 6G Systems. So I will read my short biography. I am a professor and the director of the Department of Sciences and Technology from Universidade Autónoma de Lisboa. I am a researcher at Instituto de Telecomunicações in Lisbon, Portugal. Between 2005 and 2008, I was with the NATO Air Command and Control and Management Agency, NACMA, in Brussels, Belgium, where I managed the implementation of the deployable communications of the new Air Command and Control System program. I was involved in multiple computer networks and telecommunications projects. My research interests include networking and mobile communications, namely transmission techniques associated with 6G systems. I am author of 5 scientific books from CRC Press, and the author of several dozens of journal articles and conference papers, and a senior member of IEEE. So we had a very excellent presentation about 6G systems, and my presentation I will address initially the society. So my presentation will be top down. First, I will speak about the society, then I will address the 5G communications, and finally I will speak the transmission techniques used in 6G systems. No, therefore not the 6G communications as a whole, because this was already addressed by Professor Shahid, but I will speak specifically about the transmission techniques of the 6G systems. So the references for my talk, I have 5 journal articles about 5G and 6G systems. This article, October to 2020 about 5G communications. This one is about in advanced of 5G communications, April 2021, September 2021, about also about NOMA, non-orthogonal multiplexers for advancement of 6G communications. And this journal article published December 2022 about 6G, about transmission techniques for 6G communications. And this last one, which is about the transmission techniques of 6G communications, namely about the large intelligent antenna systems, which is the subject that we'll bring here today. So initially, I will speak about the digital transformation. What is the society right now? 5G communications and 6G communications. So what is the society? In the past, we had several industrial revolutions. The first industrial revolution that completely modified the society and the world was the industrial revolution. The first was the steam. The manufacturers were completely modified, and this leads to a more efficient use of the resources of the society. The second industrial revolution, the revolution of the electricity, was an advance to the first one, and also the world became electricized or electricity driven, and the society, these also brought more efficient use of the resources. Finally, the third industrial revolution that started on the 40s with the analog electronics, and then the digital electronics in the 80s. Finally, the all over IP, the voice and data over IP, everything over IP. This is the third industrial revolution. The third industrial revolution is a replacement of humans by information systems and humans by information technologies. And some jobs disappear, others were created with this modification of the society. And we, on the third industrial revolution, which is the revolution of the media as well, we are in the information age. Information age is all of the information is on the internet. We go to Google and we have access to different information, and some information is correct, other information is not so accurate, and we need to know what is noise and what is correct. This is the information age. Everything is in Google. Right now, we are living the fourth industrial revolution, which is the revolution of the robots, of the artificial intelligence, of big data, the big amount of data, and Internet of Things. Instead of having people communicating, we have things communicating. And this is where the 5G and the 6G as well are located. So 5G and 6G communications address the communication of things instead of communication of people. This is the difference. And naturally, with the fourth industrial revolution, we have robots that replace humans. We have the humans being replaced by robots that are driven by artificial intelligence, etc. And we are not, as in the third industrial revolution, not at the age of information, but we are at the age of knowledge. Knowledge is different from information. Knowledge is the information at the right time given to the right person to support a decision making. So this is much more important. It's like information is, we go to Google and we have access to information. Knowledge, we go to Chat GPT and we have access to knowledge. This is the difference, because Chat GPT aims to sometimes with sometimes it's not completely accurate because it's still learning, but aims to create knowledge, not information. So the fourth industrial revolution, as I already mentioned, is the replacement of humans by robots, or also leads to a more efficient use of the resources. This is characterized by the massive use of robots, as well as artificial intelligence, big data, Internet of Things, things communicating, 3D printing, which will modify the world, the logistics chain, everything will be modified. And the quantum computing will be a reality in the near future, namely following an approach of cloud computing. So with this new society, some jobs will disappear, others new jobs will be created. So the society is being modified, and this is more important. What are the assets or the skills that are required from people? We should adapt to these new skills of this new society. Namely, we should focus on scientific, technical, and human skills, like ability to communicate, to write, ability to manage conflicts is very important, to work in team group, to work in groups, in teams is very important. So emotional intelligence is very important. Abstract thinking, these are assets that are more and more important. And in this new world, the business is also being different, more and more different. Why? Because companies are becoming more and more technology demanding, which means that companies are becoming more capital intensive. Okay, since if they need more, say, if they are more dependent from technology, therefore they are more capital intensive. So this will put a problem. This will be a problem in the future for the small companies. Small companies, without having a big amount of funds, will have constraints in terms of entering the market. So what is a robot? Let's think about an autonomous vehicle. An autonomous vehicle can be viewed as a robot that moves. Instead of having legs, it has four wheels. It moves, and it has sensors, and it communicates with the other cars using Internet of Things. And these sensors and these communications create a big amount of data, big data. So we speak about Internet of Things, and we speak about big data. This big data is processed by artificial intelligence, and the artificial intelligence gives orders to the car to speed up, to turn left, turn right, to brake. So this is the future of the mobility. And so therefore, when we speak about robots, we speak about artificial intelligence, we speak about big data, and we speak about Internet of Things. So the society, the future society, is being modified very rapidly, even faster than expected. If we look into the artificial intelligence, the achievements that were expected to be achieved in 10 years were reached in 2 years time frame. So the world is speeding up very rapidly. So we see here, in terms of logistics, in terms of agriculture, in terms of manufacturers, in terms of medical and lawyers, in terms of smart cities. So this will modify our world. So 5G communications is a reality right now. So what is the difference between the 5G communications and the previous generations? The 5G communications, the big difference is is Internet of Things. So 5G were designed to support Internet of Things instead of communications between humans. Moreover, the 5G communications can establish communications without a base station. This is another difference with regard to the previous generations. Naturally, the speeds that are, or the data rates that are achieved with 5G communications are much higher than the previous generations, and the latencies are lower. So we achieve speeds such as 20 gigabits per second, nomadic access. And 5G communications, we have three different use cases. The first is enhanced mobile broadband, which is the regular communications, more with higher data rates. And then we have ultra reliable low latency communications. Ultra reliable means that these are type of communications that was specifically designed to support services that demands ultra reliable communications. That is very low bit error rate, does not support errors. Errors are not accepted. And low latency communications means that communications needs to be very low delay. Services that makes use of these ultra reliable low latency communications, for example, remote surgeries or autonomous vehicles. Vehicles needs to communicate, not the actual the vehicles we have right now. Vehicles we have right now is, for example, Tesla. We has an autonomous model that everything, all of the decision making is based on is vision cameras associated to artificial intelligence. So the future of autonomous vehicles is cars communicating. So this will be supported by 5G communications. And finally, the third use case is the massive machine type communications, which is the use when we need to have billions of devices communicating. For example, in smart cities or smart logistics, we have billions of sensors that need to communicate. So these sensors communicate very from time to time. They are not always communicating. They only communicate from time to time, and these devices are integrated or interconnected using 5G communications. So we have different releases of 5G. The first release of 5G is release 3GPP release 15. Which focus on enhanced mobile broadband, the one we have right now in Portugal. And then we have the 3GPP release 16, which focus on the other two use cases, massive machine mobile communications and ultra reliable low latency communications. Now, how are these different use cases implemented? These different use cases are implemented using the so-called network slicing. Network slicing is splitting the resources of the network and reserving resources for different group of use cases. That is for different services. And finally, the release 17 relies on improvement of ultra reliable, improve of network slicing, remote control of vehicles, and how, in terms of transmission techniques, how do we achieve these 5G requirements? The 5G requirements are achieved with two different, very important factors. the first massive MIMO systems. Massive MIMO systems means that we have MIMO stands for multiple input, multiple output, stands for different flows of data between each transmit and each receive antenna. Massive MIMO means that we have hundreds or thousands of transmit and hundreds of or thousands of receive antennas. And we have hundreds or thousands of different flows of data from the transmit or from the transmitting into the receiving antenna. Okay, this is one way to increase the throughput made available by 5G. The other factor that potentiates the reaching such high throughputs is millimeter wave communications. Millimeter wave communications means that we use frequency bands of the order of 60 or 80 gigahertz. Means that with such high frequencies, the coherence channel bandwidth is much higher, which means that the data rates that can be available are also higher. The problem with these such high frequencies are the range that can be achieved. The range, we know that higher frequencies, with higher frequencies, we have lower range. Why? Because the propagation paths or propagation losses increase with the frequency. So this is a problem. For example, at home, we have the Wi-Fi with 2.4 gigahertz and 5 gigahertz. With 5 gigahertz, we have a higher throughput, but a lower range. With 2.4 gigahertz ISM band, the range is higher, but the throughput is lower. So there is a trade-off. There is always a trade-off with this. In any case, with higher frequencies, when we speak about MIMO systems, we speak about using, or when we speak about millimeter wave communications, when we speak about higher frequencies, means that the antennas size are lower. Using MIMO systems, the distance between antennas are of the order of 3 to 4 wavelengths for the signals to be uncorrelated between adjacent antennas. Means that in case we use 80 gigahertz, means that the wavelength is lower and the size required to accommodate a MIMO system is much lower because the wavelength is lower. So millimeter waves fits well with MIMO systems. So 6G communications. So as we have seen, the initial requirements, the 5G aimed or focus on the implementation of the fourth industrial revolution, namely in implementing the Internet of Things. Internet of Things was the keyword of 5G communications. So supporting, for example, communications between vehicles, communications between devices, not between humans. 6G communications that are expected to be reality by 2030 aims to improve such requirement, as we have seen in the previous presentation from Shahid. We will have, for example, holographic services, extended reality and augmented reality, smart cities in a more massive way. Instead of having a video teleconference, we will go for holographic services. And for this, we need more and more data rates, and 6G focus on this. So 6G is expected to be a reality by 2030, and we know that each 10 years, we have a new generation of communications. The first generation of communications started or came on in 1980, only for voice, analog voice. In 1990, the GSM arrived, And in the 2000, 3G was a reality. In the 2010, 4G brought us new services like massive use or massive access to social networks. In 2020, we have 5G communications, and in 2030, 6G will be a reality with more and more services. Okay, so we know already some services that we want to achieve, but we also know that when we have resources, new services will arrive. So this is a two-way, let's see. So with 6G communications, we will achieve, we aim to achieve at least 1 terabit per second, nomadic access, in mobile environment, 1 gigabit per second, and spectral efficiency much higher. That what is a spectral efficiency? The spectral efficiency is the number of bits per second that is made available in each hertz of the bandwidth. And all of this is achieved using, in terms of transmission techniques, using terahertz bands and visible light communications. So we speak about even higher frequencies than those millimeter waves utilized by 5G communications, and using large intelligent antenna systems. So what is large intelligent antenna systems? Large intelligent antenna systems is like a panel that we have a panel where each panel, we have over there, we have 12 panels, where each panel has a number of antennas on board. And by using these high number of antennas in different panels, we create a beamforming. What is a beamforming? I'm going back. That's it. It's here. So beamforming is a technique that has been used many years ago. So initially, it was used by phased array radars. So we have different signals, like different antennas. But in this case, while in MIMO systems, the antenna elements are typically separated 3 to 4 wavelengths. In beamforming, the antenna elements are separated half wavelength. And by combining the signals properly weighted, that is being sent to each of the different antenna elements, we create a beam where we maximize the signal-to-noise ratio towards the angle and elevation angle and azimuthal angle and elevation angle, so we can focus the beam towards a certain user and minimize the interferences that came from different directions. So this is the advantage. So the aim of the beamforming is to maximize the signal-to-noise ratio. So this is more or less what is implemented by large intelligent antenna systems in 6G, with some differences. So this is more intelligent, as the name states. So just before I explain in detail what is the large intelligent antenna systems, so the 6G aims to use the least system between the base station and the user. Therefore, the different users will communicate with the base station either directly or through the large intelligent antenna systems. So when there is a least system, therefore the signal-to-noise ratio is highly maximized, and it will have priority over the direct connection. So the least system corresponds, we can see the large intelligent antenna system as a behind massive MIMO systems utilized in 5G. In this case, the number of antennas is much higher than massive MIMO used in 5G, and we can see the large antenna systems as a near field beamforming, near field beamforming, because normally the communications are established in the far field, that is behind 4 or 5 wavelengths. In this situation, this is a different beamforming, because in this case the communication is established in the short range, in the near field. Okay, what is the advantage of this near field beamforming? The advantage is that the communications behaves completely different. One or the difference of the near field communications is that while in traditional beamforming, we can towards the beam in azimuth and elevation by using near field communications. We can focus also in different range. That is, let's suppose that I'm focused that direction and we have a number of different users that are aligned in different distances. And by using a near field beamforming, by using large intelligent antenna systems, I can transmit a signal to a certain user without generating interference in the other users that are aligned in the same azimuthal angle, in the same elevation angle, but in different ranges. Is a little bit like using a lens that we focus the beam. We focus the beam of the sun towards a piece of paper, and we can make fire on this piece of paper. We should have the lens at a certain distance for it to be reality. Okay, and the near field beamforming, that is large antenna systems, behaves more or less the same. So another advantage of the large intelligent antenna systems is that in same situations, channel estimation can be avoided. Why? Because equalization can be avoided. Once we don't need equalization for some receiver types, therefore we can get rid of channel equalization. So I will show you some results, some Monte Carlo simulation results for large intelligent antenna systems. So the bit error rate as a function of the ABO-Vereno, the signal-to-noise ratio, using SCFD transmission LDPC codes, 5 statistical equal average power pass, and for 4 different receiver types: the zero forcing, MEM-SE, maximum ratio combining, and equal gaining combining, and for 3 different user scenarios, namely 2, 5, and 10 users. And finally, I will show 2 different scenarios in terms of lease, composed of 4 panels, one scenario with 25 antennas, and a different scenario with 225 antennas. So these are the results for a lease composed of 4 panels and 25 antennas in each panel, with 5 users, without LDPC codes, with and without equalization. What can we see from here? We see from here that the blue lines, which corresponds to zero forcing and MEM-SE, perform better than the red line, which is the MRC, and much better than the green line, which is the EGC. Nevertheless, the MRC maximum ratio combining receiver and the EGC receiver are much simpler. Moreover, by using these 2 very simple receivers, and using the LIS system, we see that the results with and without equalization are superimposed. Being superimposed means that equalization does not bring any gain. Therefore, means that channel estimation can be avoided in this situation. We see here the results for 4 panels with 225 instead of 25 antennas in each panel. And we see here that the maximum ratio combining receiver, either with and without equalization, the performance is much closer from the results with the MMSC receiver and zero forcing. Note that the zero forcing is superimposed by MMSC. In this, by increasing the number of antennas of the LIS, the performance of the MRC approaches the performance of the MMSC. This is an advantage. Once again, MRC is much simpler in terms of processing, because the zero forcing and the MMSC requires the inversion of the channel metrics for each frequency component of the channel. And the MRC and the EGC are very simple receivers. Moreover, in addition to these advantages, we may get rid of equalization in case of in the environment, in the LIS environment, without degrading the performance, and consequently channel estimation can be avoided. So here we see the difference of results for 4 panels of 25 antennas against 4 panels of 225 antennas. And we see that, as expected, as we increase the number of antennas per panel, the performance increases. Here we see the results for 2, 5, and 10 users. And as expected, as we increase the number of users, the performance decreases. And finally, we see here the results with and without LDPC codes. As expected, with LDPC codes, we achieve better performance than without LDPC codes. LDPC codes are the codes utilized by 5G communications, are expected to be used for 6G communications as well to improve the performance. Finally, the conclusions. We see that an advantage of the large intelligent antenna systems relies on its good performance and simplicity, while equalization can be avoided for some receivers, as we have seen. The performance improvement, the performance improves with an increase of the number of antennas that form the LIS and with the use of LDPC codes. All the performing better than zero forcing. We have seen that zero forcing and MMSC are much more complex in terms of processing of the receiver, because it requires the channel inversion for its frequency component of the channel. And the MRC EGC do not require this inversion. These 2 simple receivers can work without equalization, and therefore channel estimation can be. And in this study, we have seen that a system comprising a large intelligent antenna system associated with LDPC codes and coupled with SCFD transmission techniques achieves performance optimization that improves with an increased number of antennas. And I take this opportunity to advertise a special issue of MDP that are open for submissions. So anyone that is doing research on this area is invited to submit a manuscript to this MDP, which is the second quartile, is a very good impact factor, and is open access. And these are my CRC books published. And thank you very much. And right now I'm open for questions that you may have. Thank you. So, of course. Otherwise, I would ask a question to myself.
Hello, the first question is like, the groundbreaking technology of 5G is the massive MIMO. So you think that it will be also, apply in the 6G in a similar way?
Sorry, could you?
Yeah, so the groundbreaking technology of 5G, groundbreaking, the main kind of the technology of 5G is identified as the massive MIMO. So you think that this, it will have the same role in the 6G as well?
Yes, of course. I think 6G communications were achieved with massive MIMO, and by using higher frequencies than the regular 2 to 3 gigahertz. So with millimeter wave communications, using the frequency bands of the order 60 or 80 gigahertz.
Yeah.
Why? Because the coherent channel bandwidth is higher, which means that we can the throughput made available is also higher.
Yeah.
But in 6G, the throughput that we need, the throughputs that we need are higher, which means that we need to go behind massive MIMO. The large intelligent antenna systems means that we the number of antennas is even higher, can be viewed as a behind massive MIMO on one side, and on the other side we continues increasing the frequencies, like making use of terahertz bands, the frequencies of the order of many gigahertz up to 10 terahertz, which means that once again we have an increased coherence channel bandwidth, and consequently we can support higher throughputs. So I think the trend is the same. The trend is exactly the same. And the large intelligent antenna systems, by using these short range beamforming, brings advantages.
Yes.
That's it.
Yeah. The second question is, you talk about with the I can't remember, it's a 4G or 5G, that there are a few social skills, right? Like emotional intelligence, abstract thinking. So how it transformed to the 6G? I think it's quite interesting how the human evolution, is matched with the technology, right? So I think in this slide, Samya, you mentioned about the emotional intelligence, the socio impact.
Yes.
Yeah.
Well, yeah, I think society is being modified every day. Every day. So people is being replaced by robots. And so these routine tasks, we don't need people to learn how to develop routine tasks. We need people to make use of artificial intelligence to make decisions. Let's say, I think humans are more and more at eye level.
Yes.
And what are the skills to be at eye level? This is the skills that we need to be at this eye level, because at low level we have tools, we have information systems technology, we have artificial intelligence. So we in these skills, it's as I mentioned, our skills, the skills for the future is emotional intelligence, critical thinking. Think out of the box. We need to think out of the box. Communications, writing and oral communications is very important, more and more. As I mentioned, these conflicts, social conflicts, we need to, very often people is fired not because of being incompetent, but most of the time because of conflicts. Conflicts management is very, very important.
Yeah.
So that's it. Yeah, that's abstract thinking is also important.
Thank you. Thank you, Mario.
No more questions?
Regarding the time frame that you showed us for the 6G be productized, so you mentioned 2030, wasn't it? Do you think it will be that way?
Yeah, I think right now the discussion is about the requirements that needs to be achieved. What are the requirements, and then what are the solutions? The research community is already studying the solutions for these requirements, but the requirements are still not closed. So first we need to finalize the requirements, and then we will address the solutions in terms of research that can fit such requirements. But I think 2030 and 30 is I think this we have seen a time frame of the 6G roadmap for 6G in the previous presentation by Shahid with prototypes, etc. And I think we are on the good way to have 6G communications in the 2013. Most likely, like 5G communications, we did not have the 5G at once. For example, in Portugal, we have only the enhanced mobile broadband. We still don't have the other two use cases to support autonomous vehicles, for example, or smart cities, and most likely it will be the same. We will have a first version of 6G, and the other developments will come afterwards. Yeah. Okay. So right now we skip into the third presentation. 1 second. So the next presentation will be given by our colleague Nalin, Professor Desh Nalin Jayakodi. The title of the presentation is Age-Aware Green UAV Wireless Networks. UAV stands for Unmanned Aircraft Vehicles. And his biography, Professor Desh Jayakodi is a senior member of IEEE, fellow IET, and received a PhD degree in Electronics and Communications Engineering from the University College Dublin, Ireland in 2014. He received his master's degree in Electronics and Communications Engineering from the Eastern Mediterranean University, Turkey. He was ranked at the top 2% scientists in the world in 2021 and 2022 by the Stanford Elsevier list. In 2021, he received the Presidential Award for his outstanding research performance, among many other awards and recognitions. Since 2022, he is a professor at the Lusófona University, Portugal. He held visiting and or sabbatical positions at the Center for Telecommunications Research University of Sydney, Australia in 2015, and Texas A&M University in 2018. He was a visiting professor at the University of Jyväskylä, Finland, both in 2019 and 2022, within the framework of the Academy of Finland. He was served as a visiting professor at the University of Juiz de Fora in Brazil in 2019. From 2019 and 2022, he has been a Spark professor at the Department of Electronics and Communication Engineering, National Institute of in India, within the framework of the Minister of Human Resources in India. From 2014 up to 2016, he was a postdoc research fellow at the University of Tartu, Estonia, and the University of Bergen, Norway. From 2016 to 2021, he was a professor at the School of Computer Science and Robotics, National Research, Tomsk Polytechnic University, Russia. From 2019 up to 2022, he served as the Dean, School of Postgraduate Studies and Research in Sri Lanka Technological Campus, Sri Lanka. From 2021-2022, he was with the Department of Engineering and Computer Science, Autónoma Tech Lab, Universidade Autónoma Lisboa, Portugal. He is supervising 15 PhD students and many master and undergraduate students and 5 postdoc researchers. In his career so far, he has attracted nearly $6 million research funding from many international grant agencies and has published nearly 200 international peer-reviewed journal and conference papers and books. Professor Jayakodi has received the Best Paper Award from IEEE ICC MIT in 2017 and the International Conference in Emerging Technologies of International and Communications, March 19. He received the Distinguished Researcher in Wireless Communications Award in Chennai, India, 2019. Professor Jayakodi received the Presidential Award for Outstanding Research Performance in the year 2021. He also received Best Publication Award at Sri Lanka Technological Campus, Sri Lanka, in 2019 and 2020. So, and I could speak for the whole day about you, and the floor is yours, Nelly. Thank you very much.
Bom dia. So thank you very much, first of all, Professor Mario, for inviting me to speak in this workshop. And it is always nice to be here in you all. So I think we must all thank Professor Mario for organizing this workshop single-handedly. It is not easy, you know, to organize such an event. It requires a lot of time and efforts. So without further delay, I will get into my talk. So my talk is on the unmanned aerial vehicle wireless communication, and I will share some of the recent results that we did in our team. I think I'll skip some of the slides since previous two speakers talk more on the 5G and the 6G, so I don't want you to get too much bombarded with the same. But one thing I will just tap on to this as a gateway for my talk, like how the 6G will integrate with the drone-assisted wireless communication. One of my colleagues, says that drone mania. So now everywhere there is a drone wireless communication, and it is not, second to the wireless as well. So the drone is everywhere, so we can't forget about it. And so we came up with this, 6 features of the drones that would support the main idea of the 6G wireless. So one of them is the connectivity. So when we have the number of drones that support the connectivity, and then it also support the network slicing. I have a different slide to talk about the network slicing because at UAL we have a FCT project that is fundamentally on the network slicing, and it offers the coverage of it extending the coverage of the 6G wireless that is expected to achieve. And edge computing is something that I mean the UAV can support. In the edge computing, I think some of you know, for example, at UAL, let's say we like to hear the songs of Lady Gaga, and in some people in Lisbon may like different singers. But since we as a community we like this particular singer, so it's easier for the local servers nearby this area to store them, and then have them stored in a local service. So whenever somebody needing, it can be retrieve those files from the local servers. That reduce the latency. So the drone can be used for the edge computing activities as well. Of course, when we are moving from one generation to the new generation, so we have a traditional set of issues need to be addressed. I think Mauri also talked a few of them, and then the first speaker mentioned other activities. Like the security and privacy is very much of concern for any wireless communication. But what I think is from the 6G, I believe that the green communication will be of more interest, because I think the in the 5G also it was there, but we developed many algorithms and the architectures and methods, but probably some of them were not so much keen on the energy efficiency of that particular network. So I believe that the 6G communication will be resting upon partially on the green aspect as well to make, because it's dollars, no? Everything is at the end pinned down to the value of dollar. So so I think it's important for us to think about the green aspect while we are developing new algorithms. So I think since the UAV is quite famous now, we are using UAV for as a relay and as an aerial base station. It can be also used as a data sink. So so the data sink people used in large agricultural field to collect the data, and it can talk to small sensors and they gather the information in a mission critical applications as well. So one of the application that we studied with the drone is the on demand transport. In a disastrous situation, the drone can be used as on-demand support, because when the traditional infrastructure collapse, so the drone can come into play. My talk, I think, also requires, because I'm trying to promote this green communication, so I should also talk about the Nikola Tesla. He's a Serbian scientist who migrated to US, and he's the first one to investigate or to give the idea of the RF energy harvesting. So meaning that to treat an electrical signal as a source for energy, as well as a source of the information. So traditionally, we know electrical signals can be used for information decoding. But Nikola Tesla came up with the theory of RF energy harvesting, where we can use those electrical signal to harvest energy as well. So with the wave of the 5G, people start thinking on, I think the Nikola Tesla, introduced the wireless power transfer technique, but with the discussion of the 5G, we start thinking on how, without damaging the primary focus of electrical, radio signals, how we can also harvest energy from that. So that's how this, the new technology called simultaneous wireless information and power transfer came into the existence. So in this swipe technique, we treat electrical signal as the source of information as well as the power. And but the wireless power transfer, we are using now for iPhone charging and also for these Tesla cars they're using. And that those applications are more near field applications. But as wireless, the network engineers, we like more far field applications. So for the far field also, we could use wireless power transfer, but wireless power transfer does not give the full-fledged of, the expectation of a telecommunication industry. So therefore, we move to the simultaneous wireless information and power transfer. In swiped, there are 4 main architectures in the literature. This is one of our paper that actually received one of the best reading of the IEEE Communication Society. So in this particular paper, we talk about 4 main architectures, and then what are the future architectures to come. So in the previous architectures, they were more on the let's say manual, like it's not with the AI or anything. So we use time switching architecture and the power splitting as the base. So in the time switching architecture means that a portion of time will be allocated for information decoding and another portion allocated for the energy harvesting. And when it comes to the power splitting, the power will be split upon the energy harvesting and the information decoding. And likewise, there are a few architectures, and also in this particular work, we discuss about how the future would be of the swiped. And so, there is no free lunch. So likewise, swiped also comes with a lot of drawbacks and the advantages. So one of them is it actually increased the lifetime of low power bearing electrical devices like sensors, right? Because especially sensors located in the fields where human access is limited, we can use swipe based technologies, and it requires limited maintenance, and of course it's ecological. But the drawbacks are the power scarcity. Due to the distance, the energy transfer efficiency is low, and therefore we can't really use it for a heavy or a standard level of the energy harvesting, meaning that we cannot replace the solar power with the swipe technology. And another issue can be the integration of the 5G and beyond, how the swipe can be integrated with the 5G and beyond. So when we talk about the green UAVs, so how to make the green communication more energy friendly, in the literature, we found, there are a few ways that we can do. One is the control of the transmit power, and one is the propulsion, energy propulsion models that could be used for the fixed wing and the rotary wing drones. And another technique can be the energy harvesting. So now I move on to the energy harvesting part. So this is a work that we have published in IEEE Transactions on Vehicular Technology. This is actually the first work to introduce the drones can be used, as a, swipe can be used as a viable technology in the drone assisted communication. So there was no literature available when we started this work with whether drone can be utilized, for the swiped. So in this particular work, we introduce a new energy harvesting scheme. We call it Unified Energy Harvesting Scheme. That is a combination of the wireless power transfer, simultaneous wireless information and power transfer. The third one is the self-interference exploitation. Probably, most of you are from the telecommunication area. So, interference is our traditional enemy, right? People are sitting down in this room. So we are working, we are studying, and we have our jobs going thanks to the interference. It's one of the big enemy. So the interference has been treated as adversarial factor. But in this particular work, we kind of changed the attention of the interference from being adversarial to the beneficial, because we use these interference as a source of energy. But I'll explain, like, it's not actually so easy, because that can harm the communication quality of services, right? And then we use the full duplex setup. For full duplex means, as soon as you hear the information, you transmit. So the antenna works simultaneously. The drawback of the full duplex is, while I when I talk something, as soon as I hear, I can hear my own voice. So it works against me, right? So we call it self-interference. Right, and in this particular exercise, you can see, there is a UAV on the top, and then one user is trying to talk to the UAV, and it is connected to the base station, right? So what we did in this particular work, and so the drone is working on the full duplex mode. So the self-interference we model as a fading channel. And then we apply, interference cancellation techniques, but we reduce the level of interference so that drone can tolerate it, and then use them for energy harvesting. So to achieve this, we have these time frames. So the first time frame we subdivided in between the wireless power transfer and the simultaneous wireless information and power transfer. Because base station is a heavy, device, it can energize the initial kickoff energy to the drone. So then the drone is ready for the communication. So in the first section, there will be no information transmission. It's only the kickoff energy. And then the drone started its communication in the second time slot, which is the swiped. In the swiped, as I explained, so it harvests energy as well as it engages in the information decoding process, right? And then the second time slot, we subdivided into energy harvesting and the information transmission. So the second part of the energy harvesting takes place through the swiped. So we use time switching architecture here. Now you can see we have actually two variables that we introduce, alpha and the beta. Alpha is the first window chopping. The second one is the beta, which actually determine where the right position is. Just to save the time, I will just tell you what we did in this optimization problem. So we compute outage probability here, but one of the drawbacks is we assume perfect channel information, but somebody can extend this work without perfect CSI and maybe go for the statistical CSI information. So what we did, we want to find which point the drone will have the maximum energy profile. So in order to find the maximum energy profile, we have to, just slide up, just change the position of alpha. So I see this as a sliding, and you slide, and then check which position is the alpha optimized. So you keep that alpha as the optimum alpha, and then start sliding the beta value, right? Then you find the optimal values of the alpha and beta, which minimize the outage probability while maximizing the energy profile of the UAV. Right, so I will not go into this much. So we did the CDF calculation, and then we came up with the closed form expression. This is scientific process. And then in order to, optimize the energy profile, as I said, we did the sliding, but I said in the lay terms, but we do it mathematically, okay? Right, and then we can see the performance here, outage probability versus the beta. So the K indicates the self-interference. So as I said, when the K is large, we can't really work because interference will be high. That will adversely impact the communication. Therefore, we reduce the self-interference. So we reduce to half of it, and then we go by 10%. And then 1% of the self-interference. So regardless of this, value of the self-interference, we found that the outage performance come to the local minima at the beta is equal to 0.4 through the simulation. And we also verified it from our analytical work. And we also did the test run of a drone. And we got the value for the beta to be 0.35 in the experimental. And the numerical values were 0.4 nearby. So somehow we kind of, conclude that this is a correct value. Then we kept the beta to constant, and then we went with the alpha to optimize the alpha value. And then we, got the value to be 0.1. But in the technical discussion, we realized alpha to be 0.1 is very small. So can we just get rid of from alpha and we keep the beta value just to make the system, not too complicated. But we realized that the moment we get rid of from alpha, that impact the wireless power transfer, which gives the kickoff energy, here. So the alpha goes to 0. That means wireless power transfer will be low, and that impact the entire communication. Right. So, and then we, when we do any like a new, when we introduce a new algorithm, we also have to test it with the, established papers or the techniques in the world. So we have tested this algorithm with the 3 other traditional techniques that are proposed by various scientists. One is called the Harvest-Den cooperate, which is University of Sydney algorithm, and then traditional time switching, and then the full duplex SCR. So somehow we realized that our scheme achieved lowest outage performance and also harvest a maximum amount of energy. So one of the things that we haven't checked here is the complexity. So I am not sure whether when it comes to the complexity, whether we win. So you can't win in everywhere, right? So you have to have some sort of the balance. So then we move on to the trajectory optimization. When we are moving in a car or any vehicle, our trajectory is very important to minimize the energy, right? So if you are coming from home to Yual, you have to find the best route. Otherwise, you will be spending the time, and then the money as well, right? So they both are important resources. So likewise, we wanted our drone to fly in a direction that will minimize the energy profile, but while keeping the a standard acceptable level of the outage performance. So we formulate the optimization problem, and then we solve it by our good friend Lagrangian multipliers. So you can see here the 2D view of the UAV trajectory, and then the source and the destination is here. So the blue, blue line indicates the direct position. If there is no optimization, it will go from along the blue line. But thanks to the optimization, algorithm, now first drone flies closer to the UAV, and then harvest enough energy, and then flies closer to the destination along the green line. So it is actually quite interesting to see how this drone flies, and then because it trying always to trying always to minimize the outage performance. But when we are doing this optimization problem, we have to keep like h or the height to be a standard value, because every country has a specific legal requirement that a drone cannot fly below a certain point. Right, so I think I have some more time. I will also talk a bit of the another work that we have started and we are very fascinated of. So this is the real-time monitoring and control. What I'm trying to say here is, in our traditional communication systems, which Shannon started, thanks to Shannon, we are here. And the Shannon's communication theory is to look at the communication capacity in more statistical way. But we are largely looking at the latency. I think in Mario's there's one slide on the URLLC, ultra reliable and the low latency. So 5G trying to achieve 10 to the power -9 of the reliability and the 1 millisecond of the latency. But we are in a different world that we need to see the things more faster. Like we need to look at the things more freshly, especially if you are looking at the weather information or the currency transactions. The currency change every second. So this particular real-time monitoring means like the age of information, whether we are looking at the most freshest data on our screen. So it is going beyond the idea of the latency, right? So sometimes if we are only looking at the latency, we are not sure whether we are looking at the most freshest data. So it can be, going to crowdsourcing, social media. People want to be active on the social media. They want to get the, most updated information. And, especially these Binance and the currency and these kind of areas, right? Right. So this natural question comes, I mean, why we cannot use the latency only? So the latency, in the traditional setup, we use the packet delay, we use interdelivery time. So these metrics are not on its own sufficient to characterize the freshness of the information. So we need the most freshest information. Therefore, we started studying age of information. So the next work I'm going to present is called Harvest as You Fly. So AOI in full duplex UAV assisted wireless communication. So we published this work in IEEE Internet of Things magazine. So here you can see there is a full duplex UAV trying to talk to the sensor control panel on a bottom of a bridge. So it's trying to extract the information of that particular sensor. And first there will be energy transfer from UAV to the sensor control panel. And then panel start to talk to the UAV, and that will be connected to the access point as the backhaul link. So here time allocation is divided between the T alpha and the T1 minus alpha. So you can, and what we did, so we compute the average age of information here. So average age of information is actually inversely proportional to the success probability. So we are trying to reduce the number of retransmissions. So when the more retransmissions are there, that increase the average age of the information. So there is some math here. We compute this AOI, and then we formulate an optimization problem to minimize the average age of information. So you can see here average age of information is changing when you change the alpha value. This alpha, as I said in the previous slide, alpha kind of tells you how much amount of time we allocate for the energy harvesting and the information decoding. So when the alpha is very small, you can see the age of information is high. That means you are not seeing the most freshest data. The meaning is, when alpha is small, there is a small amount of time is allocated for the energy harvesting. Therefore, therefore available energy is very limited to have a proper communication. So as the alpha increase, you can see that AOI is getting minimized, right? You achieve kind of the minimum value of AOI. And because it has enough balance between energy harvesting and the information decoding. But as the alpha increases, you can see that again the age of information increasing. This is due to the fact that more amount of time is allocated for energy harvesting and the less time for the information decoding. When there is a less time for information decoding, that requires more retransmission, right? Because the destination is not satisfied, it asking to retransmit again and again, and that increase the age of information. Then we look at how the age of information behaves with the power transmit power. And you can see that as the transmit power increase, age of information is reducing, but it reaches sort of an equilibrium position. After some time, it doesn't increase anymore. Okay, so I have a few minutes left. I will also talk about the future directions if you like to do some research in this area. And we believe that after the age of information with the 6G, it will tap on to the semantic communication. In the semantic communication, what we are looking at is the right content. So this was actually discovered by a scientist called Wiener. And Wiener came up with two fundamental questions. One is the information capacity, which was solved by the Shannon. And second is whether we are looking at the semantic content. So semantic content is is the meaning of the message, if I were to tell you, like, for example, if traditionally the destination always assume, let's say your phone always assume whatever transmit by your phone is important to you. So let's say you are receiving a call from your friend, and then your phone is assumed whatever transmit by the phone is important to you. Therefore, it's trying to decode everything. If it cannot decode, it send the ARQ messages, right? But sometimes you don't need all of the information. The secondly, that also, that may be viewed as a waste of the radio resources. Therefore, this idea of semantic communication means using the machine learning technique, it trying to identify what are the famous or the interested content to the receiver. So it's looking at the receiver's perspective. And then in this particular example is a new project that we are working on, the wildfire detection in Portugal. So here you can see that the semantic encoder is, trying to study or understand what sort of the images that are interested to the, the receiver, because if we are placing sensors in a forest, there could be a lot of images, birds moving around and the animals. But we are interested in only these, let's say the fusion, the smoke pattern of the forest, or if there is a fire and those images, right? So this encoder will train only on those areas or those images, and only those things will be transmitted to the destination. And then the semantic, part will be achieved because we are saving a lot of radio resources. And also, I think we can also tap on to the edge of information as well. And so we believe that the semantic communication married with the edge of information will propose the new URLLC, because URLLC was, blindly on the reliability and the latency only, but it doesn't look at the freshness of the data. It doesn't look at the semantic part of it. So I believe this can be a really good research topic. And the network slicing, I should also talk, since we have a project at UAL on this. So the network slicing means, so let's say we have, in this group, in this particular room, we have, maybe 10 people, and then we identify the requirement of each user. So some user may be a healthcare users, and they need more URLLC to have maybe to see a doctor in real time, or perform remote surgery. So they need to have a better, reliable links and with a very low latency. And then another users can be on the enhanced mobile broadband. They need more data rates, right? So we identify these particular layers, and then we generate the virtual layers, from our radio resources. We generate virtual layers and allocate it to these interested parties. So we will not have to, sorry, it's time up. So we don't have to allocate the entire resources to all the users. So we will be, slicing our network virtually and then allocate them. So here, one of the paper we publish on the network slicing with the UAV. So these are these virtual, network slices that we allocate for a particular users. And we think it can associate with the many other technologies. It can work with the URLLC, it can work with the terahertz communication, and the reconfigurable intelligence surfaces, and the wireless power transfer. So I think RIS Mario mentioned. So this is the other project that myself, Mario, and Professor Rui is working. Right, I think just a promotion campaign. We are organizing a conference in Edinburgh. It's called IEEE COMAD. So if you like, you can submit papers. The deadline is 31st of July. Yeah, thank you very much.
So I have a question, Nalin.
Sure.
My question is in terms of power transfer about UAV. Could you give us an idea about, for example, if you have a drone flying at a certain distance from the base station, a drone that, for example, has a capacity or has an autonomy of half an hour, how much can you increase the capacity or the autonomy of a drone by using the system that you are proposing?
Yeah, so the basically actually, amount of energy that can harvest is in the microwatts. Therefore, it will only support for a signal processing capacity. So if you want to increase the lifetime of the drone, so then we have to use the wireless power transfer. So that can actually harvest in the watts. So in the 30 minutes of the lifetime, it can increase by about 10 minutes, 5 minutes to 10 minutes of the lifetime. And if you are only using the swipe, it will not enough for a mobility of the drone. It will only enough for a signal processing. So what we're trying to do here is to make the communication of the drone as a bonus. So it will be free, there will be no energy requirement. It will engage in the communication on free of cost, right? So there will be no energy consumption, yeah. But the motion will have only few, marginal impact to its mechanics. Yeah.
Any questions? Did you get the question?
Yes, yes. So actually, this will not exclusively, be the source for the drones, transmission. Like I got to your point, like if the drone is going for 30 minutes only, it's not enough. So this is actually add-on, add-on to what is the battery supply of the drone. So it will not replace the drone's integrated the battery, but this will be add-on to the drone's, battery. So it will give an extra, percentage that the drone can be alive. So it is difficult to have a, fully, a wireless powered drone, but we can have it. Well, in Japan, they have tested. So in order to achieve this, so we have to have very strong base station to harvest energy continuously.
So does the drone have to be stationary to get the power transfer, or can it be continuously moving?
It can be continuously moving in the vicinity of the base station.
Okay.
Yeah.
Just a question. So it depends on the distance, no?
It depends on the distance. The more the distance, the lower the energy
lower the
harvesting.
energy. Okay.
So we are using here a nonlinear energy harvesting model that actually more practical, because in the linear energy harvesting models that were used in the early, like about 3-4 years ago. So when you have a more, transmit power, you harvest more, but it is not the case with the diodes. I think it has this clipping thing. So it clips, so the nonlinear energy harvesting model does not increase the amount of energy, no matter how much you increase the transmission power.
Thank you very much, Nalin, for
Thank you.
your
Thank you,
excellent
everyone.
presentation. Just to mention that this conference is being transmitted through 4 different ways. So we have people following this event in person here, through Zoom, through YouTube, and we have a website where the video streaming is being transmitted. So we have people also following on this website with the video streaming that we have created especially for this event. So right now we have 1 second, sorry. Glasses. So right now we have Professor Rui Diniz, who is a distinguished speaker of IEEE Vehicular Technology Society. And the title of his talk is A Look Behind Massive MIMO, Working with a Huge Number of Antennas. So just a reference with regard to his biography. Professor Rui Diniz received a PhD degree from Instituto Superior Technical University of Lisbon, Portugal, in 2001, and the habilitation in telecommunications from Faculdade de Ciências e Tecnologias da Universidade Nova de Lisboa in 2010. From 2001 and 2008, he was a professor at Instituto Superior Técnico. Currently, he's an associate professor. In fact, he's already a full professor at Faculdade de Ciências e Tecnologias da Universidade Nova de Lisboa. During 2003, he was an invited professor at Carleton University, Ottawa, Canada. He was a researcher at CAPS-IST from 1992 to 2005 and researcher at Instituto de Sistemas e Robótica, Institute for Systems and Robotics from 2005 to 2008. Since 2009, he is a researcher at Instituto de Telecomunicações. Rui Diniz is an IEEE distinguished lecturer and was editor for several IEEE journals, as well as Elsevier Physical Communications. He was also a guest editor for several special numbers. He was part of the organizing committee of several major IEEE conferences. He is also a member of several technical committees of IEEE Communication Society. Rui Diniz has been actively involved in several national and international research projects in the broadband wireless communications area. He has 20 PhD students currently or past, published 5 books, over 150 journal papers and book chapters, and over 200 conference papers, and has 15 patents attributed or pending. He has been involved in pioneer projects on the use of millimeter waves for broadband wireless communications, and his main research activities are on modulation and transmission design, nonlinear effects on digital communications, and receiver design, with emphasis on frequency domain implementation, namely for MIMO systems and/or OFDM and SCFD modulations. He's also working on cross-layer design and optimization involving physical and MAC sublayer and logical link control issues, as well as indoor positioning techniques. So, Rui, thank you very much for being with us, and the floor is yours. Thank you very much.
Yes, thank
Rui.
you. So I suppose you can hear me well?
Yes, perfect. Thank you.
Okay, thank you very much. So today I'll be talking about what you can expect after massive MIMO. So as it was said by the previous talks, namely by Mario, current systems work with a huge number of antennas, and massive MIMO is the central technique for 5G. So I'll try to see what we can expect after 5G in terms of number of antennas and the corresponding techniques that you can use. So here is an outline of my presentation, motivation, an overview on MIMO and massive MIMO. Then I look to systems beyond massive MIMO with emphasis on cell-free communications that I will describe later on, and some of the enabling technologies and the corresponding challenges. Essentially, we are working with in a scenario where we have a very crowded spectrum. We want to have low bit rates, larger bit rates, and we want to have a very high spectral efficiency. This picture is essentially an overview on the use of the spectrum in current systems. It's not very clear, but you can see by the different colors that almost all bandwidths are fully employed. So we need to be very efficient in use of the available spectrum. And this means having a very high spectral efficiency that's measured in terms of bits per second per hertz. And of course, you need to save power, both from practical reasons. It's not nice to have a battery that drains very fast, but also for economic and environmental reasons. The power is expensive and most of the time it's not very friendly, ecologically friendly. So first thing that you need to understand is the channel capacity. It's a very old result from the late 40s, but essentially it says that if you have some transmit power or some signal to noise ratio and some bandwidth, there's a theoretical limit on how fast we can transmit. It's called the channel capacity. It's from Shannon. And basically it's that formula that says that the capacity bit rate grows logarithmic with the signal to noise ratio. So logarithmic with the transmit power, assuming that the noise power remains constant. This can be put in a different way as a function of the spectral efficiency. This is epsilon. And essentially says that the EB over now, that's a measure of the bit rate to the noise power spectrality. That's a typical measure for computing the performance at physical layer. Grows exponentially with the spectral efficiency. So if I want to have a large number of bits per second in a given hertz of bandwidth, I need exponentially higher EB over now, so exponentially higher power. The good thing is that you have techniques to achieve this channel capacity. We have, especially in terms of channel coding, there over the last 30 years, there were huge advances in the channel coding techniques, and we have the turbo codes and the LDPC codes that perform very close to the channel capacity. Also, about 10 or 15 years ago, we had a new class of codes called the polar codes that also have performance very close to channel coding. So this means that we can use the channel capacity as a reference for designing a given communication link. Things get a bit more complex in terms of wireless communications. The channel is not very friendly. We have lots of nasty propagation effects in terms of blockage, in terms of multipass, and we end up with a channel that's frequency selective, and so this means that the channel frequency response changes with the frequency. Different parts of the spectrum have different channel frequency response, and they also have fading effects, which means that the power can drop very fast due to blockage or other effects. For these multipass channels, we already know what's the optimum receiver, and actually we already know this for a very long time. It's called maximum likelihood sequential estimation. It's also called the Viterbi equalizer. The problem is that it has a complexity that grows exponentially with the lengths of the channel impulse response measured in terms of bits. So although this is optimum, it's usually not employed because it's too complex. Most systems employ the so-called OFDM. It's actually the de facto standard for most wireless communications. Essentially is a block transmission technique where we add some proper cycle prefix to the blocks, and the implementation can be very efficiently done through the FFT algorithm that's at the transmitter at the receiver side. There's also another variant of block transmission technique called single carrier frequency domain equalization. From the implementation complexity is more or less the same. Essentially, we shift an IDFT block from the transmitter side to the receiver side. So this means that with single carrier with frequency domain equalization, we have a much simpler transmitter, but more complex receiver. And since you are working with single carrier signals, it's easier to, these signals are easier to amplify. So these techniques are particularly interesting for the uplink transmission, for transmission from the mobile terminal to the base station, because we put the signal processing effort at the receiver, and you can have a very efficient amplifier at the transmitter at the mobile terminal. But basically, these are the two techniques that are most widely employed in wireless communications. And these techniques have very good performance. There's another variant of single carrier, it's called iterative block decision frequency equalizer. The idea essentially is that with the conventional receivers who employ a linear equalizer that tries to invert the channel, the problem is that inverting a channel is a tricky operation when we have a deep fading in a given frequency. Inverting means multiplying by something that can be very large. And this either leads to some noise enhancement effects, we are also amplifying the noise, or you can lead to imperfect inversion of the channel. To overcome this limitation, we can employ iterative receivers where we repeat several times the equalization procedure. And the idea is that for each iteration, we have an estimation of the transmitted symbols from the previous iteration. And this estimate can be used to reduce the intersymbol interference and to improve the performance of the receiver. So at first iteration, we don't have any estimate, so we behave as a linear equalizer. After you have some estimates of the data, then we can reduce the intersymbol interference, and this simplifies the work of the equalizer. And you can have significant gains. In this case, with single antenna scenarios, we have gains of about 6 dB. Remember that 6 dB means that you are spending 4 times less power. So the battery lasts 4 times more, or the coverage is increased by a factor of 2. So these are relevant numbers to remember. One thing that this lead is that since you already know what's channel capacity and how to achieve that channel capacity with the proper channel coding and equalization, this means that you don't have much to research, which is a bit boring. So things were more or less like this at the end of the 90s, but then there was an amazing development that was the appearance of the MIMO systems. And this changed completely the scenario because basically we changed channel capacity. There are some theoretical results on what's the actual capacity of MIMO system, but basic idea is that capacity grows with the number of antennas at the transmitter and the receiver. So if I have 2 antennas at the transmitter and the receiver, I can aim to almost twice the capacity of having a single antenna. And this is a remarkable result that changed completely the design of wireless communications. And since the late 90s, all wireless systems, starting with the release 99 from the third generation up to now, they rely on multiple antennas. And now every mobile phone and every laptop has at least 2 or 4 antennas. So this means that you can multiply the capacity up to 2 or 4. Basically, this is critical because if you multiply the capacity, this means that you can multiply bit rate. It's interesting that you can easily extend the MIMO systems to OFDM and single carrier schemes. The problem is that the optimum MIMO receiver is too complex. Usually you don't try to have the optimal MIMO receiver because we need to have lots of processing and lots of comparisons. Essentially, it grows with the number of antennas exponentially. So in practice, you use suboptimal receivers. Mario already talked a bit about them, but essentially the ones that have better performance are the minimum square error based receivers that can have close to optimum performance and acceptable complexity. This is just an example on minimum square error receiver for iterative receivers in MIMO. And as you can see, different colors are for different iterations. After just a few iterations, we are very close to the match filter bound. By the way, this match filter bound essentially is the performance that I could have under ideal scenarios where I just transmitted one data symbol, there is no interference, nothing at all. So when something is good, we try to increase it. So if you have gains by having more antennas, let's try to put even more antennas. So this led to the massive MIMO schemes that started with the end of 4G and are basically at the core of the 5G systems. And the idea essentially is, okay, instead of having 2 or 4 antennas, let's increase the number. So say 100 antennas or even more. This picture is from the Lund massive MIMO demonstrator. I think it had 128 antennas. It had even some Guinness records in terms of spectral efficiency. And now all base stations have some different flavors of massive MIMO since they are part of the 5G. So I'd like to emphasize that massive MIMO is not MIMO with more antennas, because the techniques that are employed with MIMO don't work with massive MIMO. They become too complex, as I just said. So we need to share some common elements, some RF chains, some mixers, some quantizers, and so on. And we need to have low resolution, low complexity implementations. So this means that the quantizers ideally should have a lower number of bits, a lower resolution. The amplifiers probably won't be linear as in current systems. And also the detection can't be something like a straightforward mean square error receiver. There are also some challenges in terms of channel estimation, because you need to estimate a large number of channels for these techniques. If I increase the number of transmit and receive antennas, I need to increase the number of parameters that I need to estimate. So this is another challenge. One of the things that is critical for massive MIMO is the so-called channel hardening. Essentially, what happens is that as I increase the number of antennas, and if I perform the gram matrix of channel, essentially is this channel times its Hermitian, its complex conjugate transposed matrix, we end up with something that is almost an identity matrix. So here the red colors are things that are very large and the blue colors are things that are very low. So when I have a large number of antennas, and if the number of users is not too high, then by just multiplying by the complex conjugate of the channel matrix, I essentially orthogonalize the users, especially if the correlation of the channel is not too large. So this rho is the correlation between different antennas. And this is the key technique that enables massive MIMO. This channel hardening means that we don't need to perform complex matrix inversions to detect the different data streams. And this leads to implementations. Mario already talked a bit about this, like maximum ratio combined array ratio combined receivers, where with just a few iterations, you can have almost optimum performance without the need of channel inversions, as in zero forcing on minimum square error receivers. Another interesting advantage of massive MIMO is that the interference terms tend to be relatively low, tend to have a relatively low correlation between different antennas. And we can take advantage of this to make the systems more robust to imperfections like nonlinear effects. For instance, in this case, we are studying the impact of low resolution quantizers, in this case, digital to analog converters. And it can be shown that the ratio between the signal and the nonlinear distortion for a MIMO system grows with the number of transmit antennas. So if I have more transmit antennas than the receive antennas, this is a kind of rounding transmission. we have a higher signal to interference ratio. This means that in practice, you can have quantizers with just 1 bit. Actually, it's 2 bits because it's 1 bit for the real part and another for the imaginary part. But this means that instead of employing quantizers that are difficult to implement, typically with 8 or even 10 bits, you can employ just 1 bit quantizers at the transmitter and still have very good performance. I'd like to point out that to have an acceptable performance with typical channel coding schemes, we need 10-15 dB of signal to interference ratio. So this means that it's relatively easy to achieve this 10 to 15 dB by just increasing the number of transmit antennas. So this means that you can have a very large number of antennas, but you want to have something that's relatively simple to implement. There are several approaches to achieve this. One of them that I particularly like, it's called multi-layer architecture. Essentially, we can have several layers of antennas and different layers for different purposes. So you can have a first level of antennas with antennas very close together that are just used to simplify the power amplification. We can have amplify a variable envelope signal as the sum of constant envelope components, and each one with an associated antenna. Or we can have also some more sophisticated amplification techniques like link amplifiers and quantized digital amplification schemes, where we have multiple amplifiers to together amplify almost linearly the signal. The second layer, typically with antennas spaced by half wavelengths, is for beamforming purposes. So creates beams in specific directions, as Mario mentioned, with inherent advantage. Then we have a third layer that's for spatial multiplexing purposes, like in a conventional MIM. The blocks of antennas for this third layer need to be relatively far apart because they should be with low correlation. Another approach to simplify the implementation of massive MIMO is by employing hybrid analog digital architecture. So essentially, we have some pre-processing matrix at the transmitter side, that's called W, and some detection matrix at the receiver side and the channel in between. And instead of having a huge matrix, we split this as product of two matrices, one digital matrix and one analog matrix. The analog matrix just performs phase rotations and is relatively large. And typically it's common for all bandwidths. The digital matrix is a bit like a conventional MIMO matrix, either for the transmitter or the receiver, which performs the rest of the separation of users. And these digital matrices need to change from subcarrier to subcarrier or from frequency to frequency. And there are different ways you can have this fully connected matrix or just partially connected to reduced complexity. Here is just an example where you compare full connected and partially connected. Full connected is the green, partially blue, with digital one. And as you can see, after having just a few iterations of the receiver, you can have almost the optimum performance with the fully digital. That's much more complex. Okay, so basically this is the scenario that we have now, and current systems are working typically in lower frequencies, and there's a trend to increase the frequencies, the working frequencies, so from sub 6 gigahertz to millimeter waves, terahertz, and so on. So this means that as you increase the carrier frequency, you can reduce the antenna size. So you can have a larger density of antennas in the same area. So this means that you can even go beyond the huge number of antennas that we have in massive MIMO. So that's the next step that I'd like to describe. There are different ways of working with a huge number of antennas. Mario already made some remarks and some comments on these techniques. So I'd like to emphasize one of them that's getting more and more popular. It's called cell-free systems. So essentially, you can imagine that we have a huge number of antennas spread over a very large area, some they can be fully equally spread or concentrated in some points. And the idea is that, okay, by having all these antennas working together, we can skip the concept of having cells as in a typical wireless system. So we remove the concept of cells, you put everyone communicating at same resources, same time, same frequency. And the idea is to separate the different signals through the antenna. So we perform some spatial separation instead of the conventional time frequency separation of the signals. This separation can be done at the access point level, which can already be a typical massive MIMO system, or at some central processing unit that's connected to some or all access points. And basically, each user can be connected to different access points, to one or more access points. And this creates what's called macro diversity. So essentially, if one of the links gets some blockage or has a deep fading, since the user is served by multiple access points, then we are able to still maintain the quality of the link. And as I said, the separation of users can be done either locally, which should be ideal, or as at a central unit that's a bit more complex, but has better performance. So having in mind this goal of cell-free communications, let's take a look on what kind of enabled technologies do you have or can you take advantage to achieve these goals. The first thing that comes to mind is intelligent reflective surfaces or reflective intelligent surface, so IRS or RIS or whatever. Essentially, it's a surface that's full of antennas. Usually they call it meta atoms, these antennas. And these antennas receive a signal and transmit exactly the same signal that they received. They just change the phase and eventually some delay if necessary. And the main consequence of this is that by playing with the phase of the transmitted signals by the surface, you are able to create reflections in any direction that you like. So we skip the Snell law that says the angle of arrival and angle of departure needs to be the same. So you can have a signal arriving in 5 degrees and the departed signal at 20 degrees, and eventually you can create nulls in some specific directions. So we can focus the energy in one direction. This allows very efficient interface management, a bit like an adaptive beamforming. The good thing with this technique, that's why they are so popular, is they have relatively low complexity because these antennas just receive and transmit the signal, eventually amplifying. So it's a bit like some relaying from the early 2000 years. And they can lead to very good performance. The problem is that to be effective, these IRS surfaces require channel knowledge, and it's very difficult to estimate the channel when we are working with passive elements. So if the antenna just receives and transmits, don't do any processing at all, it's very difficult to estimate what's the actual channel. So this led to some different approaches, but still playing with a huge number of antennas. The one that's probably the most ambitious, it's called large intelligent surfaces, as Mario described. This figure I'm stealing from the original papers on on this technique, but I like it because it presents exactly the concept. So we have a surface, this wall, with a huge number of antennas, and the idea is that I don't activate all the antennas for a given user. I just activate the antennas that are relatively close to that user. Moreover, depending on the quality of the channel and the required bit rate, I can activate more or less antennas. So you can imagine as the user is moving, the number of antennas that are being activated will change. This is probably the ideal scenario in terms of communications. To make everything adaptive and changing, so you can imagine that you are surrounded by antennas, and only the antennas that are close to you are used for yourself. Since these surfaces are designed to be very large, so most of the traditional approaches for studying propagation channel need to be redesigned. First of all, you are at short range communications. You are in near field communication, so the far field approximations are no longer valid. But we have an advantage that we have line of sight almost for sure because of the physical characteristics of the system. So the communication becomes a kind of spatial domain resource allocation. One of the challenges is to know which antennas should we activate as we are moving. So this means that some of the traditional challenges disappear, others arise. By using this concept, we can start thinking in terms of communications in a completely different way. First of all, you can use this large intelligence surface for positioning. Since different parts of the antenna have different angles of arrival and angle of departure, then you can use this to make an accurate positioning. So you can use, the edges of the leash to obtain the direction of propagation for a given user, and with this obtain the position very accurately. So this means that you can envision a wireless communication scenario where you also know the exact position of each user. And as I said, of course, you can, by knowing where the users are, you just create adaptive beamforming for those users, and you can select easily which are the areas of the antenna, the list that are activated for each user. Of course, this means that you reduce a lot the signal requirements for establishing the communication. And you can expect large capacity gains and some robustness against interference because you are making directive beams for different users. Professor Nalin already told about energy harvesting. This is an interesting application of the large intelligence surfaces. You can create a beam of energy to a given device, and this would enable charging more than the typical centimeter distances that most wireless power transmissions techniques allow. Of course, there are some biological effects. No one would like to be between the leash and the device if you are transmitting a very high power beam, but at least you have this potentiality that could be taken advantage and to allow to rethinking the energy harvesting techniques. As you can imagine, if you are talking about, say, 10,000 antennas, it's not feasible to put them in a specific device, mostly for economic reasons. So it makes sense to split these leash in panels, say each panel with 100 antennas or something like that. Notice that 100 antennas might be very large for systems working at small carrier frequencies, but for larger frequencies, having 100 antennas, it's relatively simple. You just can imagine that digital camera behaves as a kind of antenna for the image, and the number of pixels is much larger than 100. So as you increase the carrier frequencies, it's easier to put more antennas in a given device. By splitting in panels, you can dedicate some panels for each user. You can imagine that each panel has a number of users that's able to separate, say 2 or 4 or something like that. And once again, you can take advantage of the position to simplify the allocation of users and need to make this more or less adaptive according to the user's localizations. That's another interesting technique that this is from Ericsson. It's called the radio stripes. Over here we have a picture with just a first set of antennas from a radio stripe. These lines in the bottom are essentially the cables that power the antennas and exchange signals between them. And you can they made this in such a way that's a bit like gluing some duct tape to a wall or something like that. So you have a stream of antennas. That's why they call it the radio stripe. And they're all fully connected. We just cut the part that you want, glue to the wall or to the edges of your building or whatever. And then by this, you just implemented a distributed massive MIMO very efficiently and very cheaply. You don't need any qualified, any specific qualification just to implement this. You just need to make sure that the links are connected in the right place. So this is a way you can imagine the radio stripes. They could cover the ceilings of a room. It usually makes more sense to put them in the ceilings just to make sure that you have line of sight propagation. And as with the lease, we can split this in panels. These won't be panels, it would be, say, rulers or something like that, just segments, just to make it more practical to manage. After taking a look on the technologies, let's just see some open challenges that you need to take into account. First of all is the transmitter and the receiver design. You need very low complexity transmitters and receivers. It's reasonable to assume some on-off approaches where some antennas, some parts are not activated, they are just activated as required. We need to combine this with efficient beamforming. One thing that you are still studying is if we can skip the equalizers. By having a large number of antennas, it might be possible to work without equalizers, and this would simplify a lot all the processing. You also need how to manage the interference cancellation, and it would be desirable to have low resolution quantizers, low resolution amplifiers, and so on, just to reduce the costs. Channel estimation is one of the biggest challenge for these distributed massive MIMO systems. There are too many channels to estimate. And the typical channel estimation techniques are not suitable. Usually when I'm estimating a channel, the idea is that all the other transmitters are shut off, and then I transmit the training sequence, then do the same for the second transmitter, and so on. And this is not feasible when we have a large number of channels to estimate. There are some approaches that take advantage of reciprocity of the transmit and the receive channel to reduce the channel estimation complexity, but still this is a big challenge. I think the most promising techniques are parameterized channel models, where instead of estimating the channel, we just estimate how the channel changes, say the Doppler drift and the starting point of the channel for each multipass component. There are also some interesting techniques in terms of position-assisted channel estimation, where we take advantage of the knowledge of the user localization to estimate the channel. And this opens the door to some more advanced techniques like machine learning techniques to estimate how the channel is changing and when do you need to send new training and so on. And of course, you need to combine this with channel tracking to reduce the signaling overheads for channel estimation. Finally, there's an important challenge, that's the resource allocation. Up to now, the resource allocation essentially was deciding which base station and which time and frequency slot is going to be attributed to a given user. Now we create a new dimension to the problem, and it's a bit harder to address, but it's more powerful. That's the spatial dimension. So you need to know exactly how to associate the resources in time, frequency, and space in a very efficient way and without increasing overheads. And this can be formulated as a very complex optimization problem because it's non-convex and it's multi-objective. You want to maximize the sum rate, maximize the minimum rate for a given user, minimize transmit power, and so on. So this is a difficult challenge. It's asking for machine learning and meteoristic approaches. Although I think we can have some important simplifications if you combine this with positioning information, because if you know where a given user is, we already know that probably only this set of antennas will make sense for the user. So just to conclude this overview on what we have beyond massive MIMO, I just took a look on the different steps from single antenna systems to MIMO and then beyond that. Cell-free systems are probably one of the main changes in paradigm that you can expect beyond massive, beyond 5G. There are some promising techniques to enable them, particularly the LIS and the radio stripes. But we still have some challenges. So this is this will be for sure a very active research area in the next few years. So with this, I conclude. Thank you for your attention. Now I'm available for any questions.
Any questions? Rui, thank you very much for your excellent presentation. Rui is in an international conference, is out of Portugal, so we had this talk from Zoom.
From Lund.
Sorry?
From Lund, the birthplace of massive MIMO and
Okay.
large intelligent surfaces.
Any question? No? So we have finished this event, which is a conference also that became also an IEEE workshop. So it was a pleasure. Thank you for the co-organizers of this event, namely Instituto Superior de Ciências Policiais e de Segurança Interna, the place where the police officers are formed, IEEE, Institute of Electrical and Electronics Engineers, Instituto Politécnico de Tomar, and CE2, which is the research center, Autónoma Tech Lab, Universidade Autónoma Lisboa, our university. And thank you for the speakers, all of the speakers, for coming here or to give us your talks. And so thank you. I think we leave here richer with your exchange of knowledge and research. Thank you very much for being here. And thank you for the audience to be here. It was a pleasure. I think it gave you some added value for being here. Thank you very much, and look forward to be here with you in a different time. Thank you. Bye.